MapReduce fundamentals. At a global beverage company, executives wanted to analyze their global consumer feedback from surveys, blogs, emails, tweets, and Facebook comments on a daily basis. This would help them understand the beverage positioning patterns and consumer preferences of beverage flavors across age groups and in certain geographies. However, they were bogged down by large quantities of data coming in from their different sources, as well as the different forms of data constantly pouring into their systems. The sheer volume and variety of the big data received resulted in slower processing, which in turn limited their ability to make timely and fact-based decisions. One way to use this data efficiently for decision-making is to intelligently store and process it. To achieve this, the executives realized that they needed to use a method in which computing tasks could be distributed and processed across a network of a number of computing resources, leading to faster processing of data. Such a solution to their big data problem is termed as distributed computing. The company therefore decided to use HDFS and MapReduce to analyze consumer choices based on data collected daily from different sources by processing millions of data elements. The problem of data storing can be resolved with HDFS, a Hadoop file system that is the storage mechanism for Hadoop. How could distributed computing help the executives of the beverage company tackle their big data problem? Distributed computing not only allows for faster processing of data, but also enables organizations to conduct complex analyses in-house. In addition, it provides scalability that enables provisioning of more computing resources based on usage, and fault tolerance, which enables a system to continue operating properly in the event of faults occurring within one or more of its components. One popular distributed computing platform designed to work with huge volumes of data is Hadoop. Hadoop has the following primary components: the Hadoop Distributed File System, HDFS, which is a reliable, high-bandwidth, low-cost data storage cluster that facilitates management of related files across machines. Hadoop MapReduce Engine, which is a programming model that allows the mapping of tasks to different servers and the reduction or integration of responses to one result. This takes care of processing. This video will focus on Hadoop's MapReduce component. In this video, you will learn about the role of map and reduce in MapReduce and some of MapReduce's applications. The Hadoop MapReduce engine is a high-performance parallel or distributed data processing implementation of the MapReduce algorithm. This means that it can be used to write programs that can process the large amounts of unstructured data by using a number of distributed processors simultaneously. How does MapReduce achieve this function? The MapReduce model is a combination of two capabilities in existing functional computer languages, map and reduce. The map component of MapReduce distributes a job's tasks across a large number of systems. It also handles the placement of these tasks in a way that it balances the load and manages recovery from failures. The reduce component aggregates all the elements back together to provide a result. The map and reduce functions are a good choice for big data, as they do not modify the original data but create new data structures as their output. Now that we have understood the roles of the map and reduce functions in MapReduce, let us understand the characteristics of MapReduce that form the foundational behaviors of MapReduce. There are four main characteristics of MapReduce. The first is scheduling. In MapReduce, jobs are broken down into individual tasks for the map and the reduce functions of the application. The mapping is completed before reducing can begin, and the entire process is complete only when all the reduce tasks have run successfully. The next is synchronization. Since more than one process is concurrently executed in a cluster, synchronization mechanisms must be in place. This includes a function called shuffle and sort, which collects and prepares all the mapped data for reduction. The third characteristic is code data collocation, where code refers to the mapping functions. The code and data must be co-located or located on the same machine or node to ensure effective processing. The last characteristic is fault and error handling. Most MapReduce engines have error handling and fault tolerance mechanisms in place that recognize when something is wrong and make the necessary correction. Now that we have understood the characteristics of MapReduce, let us look at how it works. You know that to use big data efficiently, it is necessary to access large amounts of input data, select relevant parts from it, and to then compute something of value for businesses from these parts, all the while ensuring that the original data does not get changed. To ensure that this is done without human error, an application needs to perform these tasks. The MapReduce framework consists of a single master, which is called the job tracker, and 3 slaves, referred to as task trackers. The client applications provide jobs to the job tracker, which in turn submits or schedules the jobs to different task trackers. These task trackers then process the data. The processed data, also known as map outputs, is then forwarded to Reduce Tasks, which integrates the data from different task trackers and generates the final output. MapReduce performs its tasks in a series of steps. First, the input is split into multiple pieces of data. Then the master and workers are created and the worker processes are executed remotely. Next, the map worker uses the map function to extract relevant data and then generates a key value pair for the extracted data. When that is done, the map worker uses the partitioning function to partition the data into R regions. The master now instructs the reduce workers to contact the map workers to get the key value data for their partition. The data received is sorted as per keys, a process termed as the shuffle process. After the sorting of the data, the reduce function is called for every unique key and is used to write the output sent to file. Finally, when the reduce workers complete their work, the master transfers the control to the user program. We have just seen that the MapReduce framework uses key value pairs, KVPs, as input and output. Whatever the data, the map function extracts its characteristics of interest and presents them in the KVP format. A map worker generates a key value pair for the data it extracts. The map function extracts and presents relevant data in the KVP format. The reduce function then receives this KVP list as an input and generates another KVP list as an output. For instance, a key value pair made up of a line number and text is generated for each line in an input document. The map function then removes the line number and produces a per-line word and count pair for each word in the input line. Then, the reduce function produces word and count pairs representing aggregated word counts across all the input documents. Now that you have understood what MapReduce is and how does it function, let us review a few examples to understand the application of MapReduce. First, MapReduce can be used to track the number of times a website was accessed. In this case, the map task would be to read the logs of web page requests and make a comprehensive list. The reducer will then add them and return the result. Second, MapReduce can also be used to track how visitors arrive at a particular website or the path taken by the visitor. Third, it can be used to locate articles containing a particular word that has been mentioned a certain number of times. For instance, it can be used to locate only those articles that mention the word tectonic plate more than 10 times. Lastly, another application for MapReduce is locating the number of times a particular word is mentioned, like finding the number of times celebrities talk about a current bestseller, for instance. Now that you have learned how MapReduce works, let's evaluate your understanding. If you selected automatic fault handling, you are correct. The foundational behaviors of MapReduce include fault and error handling, scheduling, synchronization, and code data co-location. Let's do a quick recap of what you've learned in this video. MapReduce is the programming model which allows the mapping of tasks to different servers and the reduction of responses to one result. There are four main characteristics of MapReduce: scheduling, synchronization, code data co-location, and fault and error handling. The map function applies a function to each element of a database and returns a list of results. The reduce function processes several such lists of results and produces the final result.